Hey guys, tonight we slip gently into one of the strangest ideas the universe has ever offered us. Wormholes, little mathematical whispers that space and time might be able to fold and connect in ways that feel almost like magic. You're lying there, maybe with a soft glow in the room, and you imagine the night sky as a deep velvet sheet, scattered with stars like grains of salt. Somewhere out there, hidden in that darkness, could be shortcuts, tunnels through reality itself. You don't have to do anything complicated tonight. You just breathe, feel the weight of your body on the bed or the couch, and let your mind do the traveling. Wormholes started not as movie effects, but as quiet lines in equations, solutions to Einstein's theory of general relativity. In that theory, gravity isn't just a force pulling you down. It's the way mass and energy bend the fabric of space and time. When that fabric bends enough, strange shapes appear in the math, like bridges linking places that would otherwise be unimaginably far apart. Picture a sheet of paper floating in front of you, white and smooth. On one corner, you draw a tiny dot. That's you, right here, right now. On the opposite corner, another dot, maybe a distant galaxy, millions of light years away. If you travel across the paper, you plod slowly from one dot to the other, step by step, year by year. But then, in your mind, you gently pinch the paper so that the two dots touch. Suddenly, the journey is not a long trek across the sheet. It's a single breath between 2 points now side by side. That pinched fold, that shortcut, is the way people often visualize a wormhole. Of course, in real physics, there is no giant hand pinching the universe. Instead, spacetime itself, the woven blend of where and when, can curve and twist. A wormhole is what happens when that curvature links two distant regions together through a higher dimensional tunnel, something like a hidden hallway in the architecture of the cosmos. You can imagine it as a tunnel through a mountain. From the outside, two valleys look separated by rock and distance, but somewhere inside the stone, a passage might connect them. You listen to the quiet around you, maybe the soft hum of an air conditioner, the distant sound of traffic, or just the ringing silence of a late hour, and you let yourself feel how big distance is. Light from the nearest big galaxy, Andromeda, takes more than 2 million years to reach us. If you tried to go there at a comfortable, human speed, you would never make it. Hundreds of generations would be born and gone before your ship even crossed a tiny fraction of that gap. Wormholes enter the story as a question, almost a plea. Does the universe allow shortcuts, or is the vastness absolute? Scientists didn't start with glowing, swirling portals in space. They started with equations and questions. In Einstein's picture of gravity, mass tells space-time how to curve, and that curvature tells matter how to move. When people explored all the different ways space-time could curve, they found solutions that looked like tunnels. These weren't built by anyone. They were just shapes that the mathematics allowed, given certain conditions. At first, they were like sketches in a notebook, beautiful, but fragile, and not obviously real. As you imagine these tunnels, don't think of sharp Lego bricks and hard edges. Imagine instead a smooth, flowing river of darkness, a tunnel where the walls are made of pure starlight, stretched thin, where time feels a little softer, and space feels a little less rigid. You drift at the entrance, feeling that strange tingling at the back of your neck that comes when you think about something too big to fully grasp, and yet somehow calm, because you're just observing, not jumping in. The basic idea of a wormhole is simple enough to say, a connection between two distant points in space-time, like a bridge or tunnel that lets you go from A to B without crossing everything in between. But hidden inside that simple idea are deep questions. How do you define distance when the very geometry of the universe is allowed to bend and twist? What does between even mean, if space can be rearranged? You start to realize that wormholes aren't just about travel. They're about the nature of reality itself. You might smile a little, thinking of all the movies where ships dive into swirling funnels or people step through glowing circles in the air. Those images are colorful, dramatic, and very wrong in the strict scientific sense, but they carry a grain of truth. They capture that longing for the impossible shortcut, the desire to fold the map of existence and say, "Can't we just go there?" In your mind's eye, you see a ring of light hanging in the dark, like a halo made of geometry. And even though you know it's just imagination, something in you relaxes into that wonder. Tonight, you're not cramming for a test. You're not trying to memorize formulas or prove theorems. You're doing something older and softer. You're letting yourself be curious. You're lying very still while your thoughts roam across light years. The air against your skin might feel cool, or the blanket might be warm and heavy, anchoring you while your mind plays with the idea that somewhere, somehow, the universe might allow hidden shortcuts. Maybe the most comforting part is this. Wormholes, whether they exist physically or not, remind you that the universe is far stranger and more flexible than our everyday experience suggests. The ground feels solid, distances feel fixed, time feels like a one-way river. But the deeper you look, the more you find that reality is woven from something more malleable, something that can be bent, stretched, and perhaps even stitched together in surprising ways. Maybe the universe just loves to repeat patterns and build hidden symmetries, like a cosmic artist doodling in dimensions you can barely picture. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're awake enough, tell me in the comments where you're listening from, and what time it is for you right now. Are you under a bright city sky, or somewhere quiet where the stars still punch through the dark? Now, dim the lights, and let's ease into tonight's journey together. From that first shimmering idea of a shortcut, you drift a little closer to the thing beneath it all, the fabric that can bend. You don't see threads or stitching, of course. You just feel yourself floating in a dark, velvety expanse, like you're lying on your back in an infinite night. Except this night isn't just space, it's time as well, woven together into something deeper called spacetime. You imagine it first as something simple, something your sleepy mind can hold, a flexible sheet stretched out in every direction. It's smooth, almost cool, like silk under your fingers. On this sheet, you picture placing marbles, then heavier spheres, then a dense metal ball. Each one sinks a little, making a shallow or deep dimple in the fabric. If a smaller marble rolls nearby, it doesn't move in a straight line anymore. It curves around the dimple, looping gracefully as if drawn by invisible strings. That, in a gentle metaphor, is what Einstein offered the world. Gravity not as a mysterious pull, but as the natural motion of things moving through bent space-time. You let your breathing match the idea. In, space-time stretches. Out, space-time gently curves. In your everyday life, you just call it down. You drop your keys, and they fall. You sit in a chair, and you feel weight pressing into the cushions. But instead of thinking of a force reaching up from the ground, you begin to picture the Earth as a heavy sphere sitting in that cosmic sheet, bending it. You, your keys, and everything else are simply following the curves, sliding along the geometry toward the deepest part of the dimple. As you lie there, you might feel the mattress gently cradle your body, its surface giving way a little under your weight. That everyday sensation is a quiet echo of a much larger truth. Mass tells space-time how to curve, and space-time tells mass how to move. It sounds like a poetic line, but it's also the core of general relativity, tested again and again by observations of starlight bending around the sun, clocks ticking at different rates near Earth and far above it, and the delicate dance of orbiting planets. You picture a beam of light, thin and golden, crossing near a star. In your first instinct, light should go straight. No mass, no push, just a perfect line. But in Einstein's picture, that line isn't drawn on a flat canvas anymore. It's drawn on a surface that dips and sways, so the light curves too. Not because it's being yanked, but because straight in a curved world looks like a bend. Astronomers have watched this happen, measuring how starlight shifts when it passes near massive objects. The universe, it seems, really does treat gravity as geometry. Now, instead of a flat sheet, you let your imagination climb one dimension higher. Space-time isn't a literal fabric in space. It's the structure of reality itself, 4 dimensions merged, 3 of space, 1 of time. You can't see all 4 at once, but you can feel their effects. Time doesn't tick the same everywhere. Near something very massive, a planet, a star, a black hole, time runs a little slower compared to far away in the cosmic wilderness. There's a tiny, hidden lag in your phones, GPS satellites, orbiting high above. Their clocks tick differently because they sit in a slightly different warp of space-time. Engineers have to correct for that, or your map would slowly drift off course. You imagine holding a pair of clocks in your hands, one on the ground and one high up in a quiet orbit. In your mind's quiet night, you watch them tick, 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 tick. At first they stay together, but over long stretches, the one in orbit pulls ever so slightly ahead. Tiny differences, born from tiny variations in curvature. You can almost feel it as a subtle stretch in time itself, like taffy being pulled just a little unevenly. It's this bendable, stretchable quality that opens the door to wormholes. If space-time were rigid like concrete, turn it however you want, there would be no way to fold one location toward another. But if space-time can bow inward around a star, why not some more elaborate shape? If a heavy ball can make a dimple, what sort of cosmic configuration would make a deep trough that connects to another trough, like a tunnel formed by two dents touching? As you float in this mental universe, you imagine looking down at a vast, grid-like pattern lines of longitude and latitude, but in 4 dimensions. The grid begins flat, then slowly bows near a galaxy, the lines bending inward, like a net being pulled down by a weight. Where the curves are gentle, orbits are stable and familiar. Where they are extreme, you get black holes, those places where the fabric folds in on itself so sharply that not even light can escape. And somewhere in the space of possibilities, in the mathematics that describes all these shapes, there are configurations that resemble bridges, wormholes. You may feel a slight mental resistance here, like your brain is stretching the way a muscle does when you reach just a little too far. That's okay. Part of drifting off with science is accepting that not everything has to click into place. Some of it just washes over you like a soft wave. The exact equations live on chalkboards and in textbooks. You just need to hold on to the simple truth. Space-time can curve, and that curvature can, at least in theory, connect one region to another in surprising ways. Think of driving through a mountainous region at dusk. The road winds endlessly, wrapping around hills, plunging into valleys, rising again in slow, patient climbs. That's one way to cross the terrain. But every so often, you meet a tunnel, a neat, engineered hole right through a mountain, replacing 20 minutes of switchbacks with a single, quiet minute of headlights and echoing walls. The mountain didn't stop existing. You just travelled along a path where the rock happened to be hollowed out. Wormholes are like the idea that maybe space-time itself could, in some configurations, be hollowed out to connect distant places. You breathe in the thought of vast cosmic landscapes, and breathe out the comfort that most of the time, space-time behaves in calm, predictable ways. Apples fall, planets orbit, tides rise and fall in rhythm with the moon. The same geometry that allows wild possibilities like wormholes also keeps your feet on the ground and your bed steady beneath you. Maybe the universe balances on that edge between stability and surprise, giving you both a reliable world to live in and a wildly imaginative one to dream about. And as you lie there, you might notice that your own sense of time is already flexible. Minutes can feel long when you're restless, and entire hours can vanish when you're lost in a good conversation or a favorite song. Physics deals with measurable, clock-based time, the precise kind that ticks in satellites and laboratories. But your inner experience of time stretches and compresses with your feelings. In a small, human way, you are already familiar with the idea that time is not a rigid thing. The bending of space-time is the quiet engine behind everything that comes next in our journey. To talk about wormholes as gateways, we first had to feel the fabric itself. Smooth, pliable, and capable of shapes stranger than your waking mind usually considers. Maybe the universe is not a cold, empty void, but more like an immense, invisible sculpture, one that can be curved, folded, and, in rare and special circumstances, tunneled through. You float a little deeper now into the story, drifting toward the moment when wormholes first stepped out of pure imagination and into the quiet ink of a scientific paper. The night around you feels still, like a library after closing time. You can almost hear the scratch of a fountain pen, the soft rustle of pages, as if you're standing just behind two people at a chalkboard in the 1930 seconds. You don't see their faces clearly. This is more like a dream reconstruction. You see symbols, chalk dust, and a sense of restless curiosity hanging in the air. Einstein has already changed the world once by telling it that gravity is geometry, that mass and energy curve space-time. But he's not done. In this moment, he's asking another question. Can the equations of general relativity describe particles themselves, tiny points of matter, without treating them as mysterious, separate objects. You hover above their equations like a slow-moving cloud. They're looking at a solution called the Schwarzschild geometry, the one that describes the space-time around a spherical mass. At first glance, it seems to have a terrible flaw, a singularity in the math at a certain radius, a place where the equations blow up, suggesting infinite curvature. Many people took that as a physical breakdown, a dead end. But Einstein and Rosen do something subtle and clever. Instead of stepping back, they look closer and ask, is that apparent breakdown just a trick of the coordinates, a kind of mathematical mirage? In your mind's eye, the chalk lines on the board stretch and twist. The old coordinates peel away like a sticker, revealing a smoother picture underneath. By changing the way they describe the space-time, they find that what looked like a singular boundary can be reinterpreted as a kind of throat, a bridge connecting two regions. It's as if a path that once seemed to stop at a cliff suddenly continues through a tunnel you hadn't noticed. You picture two curved sheets, like twin bowls made of dark glass, facing each other. At the deepest point of each bowl, a narrow neck forms, and those necks touch, creating a continuous, double-sided surface. On one side, you have what looks like a black hole region. On the other side, another universe? Another copy of space-time? In the original interpretation, this structure, the Einstein-Rosen bridge, wasn't meant as a travel tunnel you could drive a spaceship through. It was a way to think of a particle as a kind of geometric knot, a wormhole-like bridge in space-time rather than a literal little marble. The idea hums softly in the background, matter as geometry, particles as bridges. You feel the elegance of it, like a perfectly balanced mobile hanging in a silent room, each piece suspended in just the right place. Of course, reality turned out to be more complicated. The bridge solution, once understood more deeply, did not solve the particle problem the way Einstein had hoped. But something had been born in the equations, the first clear glimpse of a wormhole. As you lie there, maybe you feel the fabric of your blanket against your fingertips, slightly rough or maybe silky smooth. That small sensory detail anchors you while you imagine space-time itself having a kind of texture, usually smooth, but with the potential to fold and join in unexpected ways. The Einstein-Rosen bridge is like the first crease on that fabric, the first suggestion that space-time might allow two distant sides to touch. You follow the bridge in your mind. Start on one asymptotically flat region that's just a fancy way of saying a place far from any gravitational sources, where space-time is calm and nearly flat. Move inward, toward the strong gravity near what we'd now call a black hole. Instead of stopping at a singular wall, the geometry guides you through a narrow throat and out to another region that looks, from far away, a lot like where you began. Two outsides, connected by a hidden inside. The image is beautiful, but the universe is not obligated to be both beautiful and friendly. When later physicists looked at this bridge more carefully, they found it has a devastating flaw for any would-be traveler. It pinches off too quickly. The throat collapses faster than anything could cross from one side to the other. In other words, this is a non-traversable wormhole. It exists mathematically, but it can't serve as a usable shortcut. If you tried to fall in, you'd slam into a singularity before you could say goodbye. Still, that first bridge matters. It's often like this in science. An early idea isn't the final word, but it changes the language, the questions, the way people think. The term Einstein-Rosen bridge becomes a poetic anchor, a name for the concept that space-time itself might contain bridges linking separate regions. You can think of it as the first sketch in a notebook that later artists will refine, color, and perhaps one day replace. Imagine sitting at a desk, drawing a simple arch between two hills. At first, the arch is thin, unrealistic, just a line. But that line tells you a bridge is possible in principle. Later, engineers will worry about materials, stress, wind, and weight. Later, they will build something sturdy. But everything begins with that first little arc of pencil lead. In the same way, the Einstein-Rosen bridge is that thin line. A first suggestion that the equations allow space-time to arch between two far-flung places. You may notice how gentle this progression feels. No one suddenly announced, "We've built a portal." Instead, two physicists, trying to understand matter in terms of geometry, stumbled on a structure that would later inspire generations of thinkers and storytellers. The bridge lay mostly in the realm of theory, a curiosity tucked inside the huge, heavy machinery of general relativity. Only later would it bloom into the modern idea of wormholes as possible travel routes. As you breathe slowly, you might reflect that this is how knowledge often grows, sideways. While trying to solve one problem, what are particles, really? Scientists trip over hints of another, like stepping on an unfamiliar shell while walking down a familiar beach. You bend down, pick it up, turn it in your hands. You don't know yet if it belongs to something living or extinct, common or rare, but you know it's worth keeping. Maybe the comforting part, as sleep begins to tug at you, is realizing that big breakthroughs don't always thunder into existence. Sometimes they arrive as small shifts in perspective, a change of coordinates, a new way to look at an old equation, a bridge hidden inside a geometry we thought we understood. Wormholes, as a serious concept, started as such a quiet shift, no flashing lights, no special effects, just a different way of reading the same mathematical story. You let the image of that early bridge linger, a narrow throat connecting two universes, or two distant regions of one universe, frozen in a timeless geometry that doesn't let anything through. It's like standing at the mouth of a tunnel sealed on both ends, knowing that in principle it reaches another valley, but understanding you cannot walk that path. For now, the tunnel is more metaphor than machine, yet even a sealed tunnel can inspire. It hints that if the rules were slightly different, if the stresses were countered, if something held the throat open, the bridge might become passable. You'll explore those possibilities soon. For the moment, you simply rest with the knowledge that deep in the heart of general relativity, long before modern special effects and CGI, the first mathematical wormhole quietly appeared as a byproduct of curiosity. Maybe the universe, in its own slow way, likes to hide treasures inside the equations we already have, waiting for someone to look at them from just the right angle. You linger for a moment at the mouth of that early bridge, hovering like a quiet observer in a dream. On one side, a universe that feels familiar. On the other, a mirrored twin. Between them, the narrow throat of an Einstein-Rosen bridge, drawn in your mind as a slender tunnel of curved space-time. It's tempting to imagine yourself stepping in, feeling a cool, weightless wind as you glide from one cosmos to another. But as you drift closer, the picture sharpens. The tunnel doesn't sit there politely, waiting for travelers. It's more like a soap bubble, caught between two fingers of reality, beautiful, but inherently fragile. One tiny disturbance, and it snaps. You imagine reaching out, fingertips almost brushing that shimmering surface. The moment you interact with it, you feel a deep instability, as if you were touching the surface of a pond made not of water, but of equations. The geometry that looks steady on paper turns out to be treacherous in time. For the Einstein-Rosen bridge, the very act of existing in a dynamic universe pushes it toward collapse. Physicists later learned to see this more clearly by extending the original solution, using new coordinates that show the entire space-time instead of just a patch. In your mental picture, it's as if someone turns on better lighting in the room. What looked like a static, eternal tunnel is revealed as something more dramatic. Two regions, connected only for a fleeting instant. A bridge that forms and pinches off so quickly that no signal, no particle, no traveler can cross from one side to the other. You can think of it like a door that slams shut the instant it opens. At one precise moment, a path exists, but any attempt to use it is already too late. By the time you try to walk through, the doorway has turned into a wall. The math says that if you follow the natural paths, the geodesics, through this space-time, anything falling in from either side is inexorably drawn toward a singularity, a place where the curvature becomes infinite. The throat you hope to cross never stays open long enough. You let that sink in as you listen to the small sounds around you. A settling creak in the building, a distant car, maybe your own breathing soft and steady. That sense of everyday stability contrasts sharply with the violent geometry near a collapsing bridge. There, time and space twist so intensely that even light cannot hold its course. Tidal forces, differences in gravity across your height, grow so strong that they would stretch you, squeeze you, and ultimately tear apart anything made of ordinary matter. You imagine dropping into the throat, in a purely hypothetical way, like a tiny probe rather than your own body. As it falls, the view outside distorts. Stars smear into arcs, darkness thickens, and the clocks on distant worlds appear to run faster and faster. Inside, however, the probe's own clock ticks along normally. From its perspective, the descent to the singularity is swift and inescapable. There is no graceful glide out the other side, no triumphant emergence into a second universe, just a one-way plunge into the heart of curvature. This is one of the universe's quiet warnings. Not every bridge the equations allow is one you can actually cross. Stability is a demanding gatekeeper. Even if a structure exists momentarily in a perfect, symmetric solution, the tiniest shove, a stray particle, a ripple of radiation, any deviation from ideal conditions can set off a chain of events that makes the bridge collapse. To picture this, you might think of balancing a pencil on its tip. In principle, there is a configuration where the pencil stands perfectly upright. The laws of physics don't forbid it, but in practice, any microscopic vibration, any whisper of air, any quantum jiggle sends it toppling over. The Einstein-Rosen bridge is like that pencil, mathematically permissible, but dynamically unstable. The slightest nudge from reality, and it falls. Physicists have studied this instability in more detail, analyzing what happens if you perturb the bridge or try to send matter through it. The results are consistently discouraging for would-be travelers. Any attempt to use the bridge adds energy and stress to the throat, and that extra burden makes the collapse faster, not slower. It's like trying to hold open a fragile door by leaning on it, only to realize that your weight is what makes the hinges tear away. As you lie there, the softness of your pillow under your head and the gentle weight of gravity pressing you down feel reassuringly moderate. The space-time around you is curved, but only gently. Objects fall, but they don't tear apart. In contrast, near an unstable wormhole, the gradients are extreme. If you dropped a long rod into the throat, the end closer to the center would feel much stronger gravity than the far end, stretching it like a piece of taffy. These are the tidal forces that make black holes so unforgiving. The more scientists learned about these early bridges, the clearer it became. If wormholes are ever going to serve as gateways, not just mathematical curiosities, they will need help. Left to themselves, under the influence of ordinary matter and radiation and the usual rules, they buckle and snap. To keep a throat open, something extra seems necessary, something that pushes back against collapse, like scaffolding propping up a tunnel that wants to cave in. You might feel a small, surprising comfort in this harsh result. It tells you that the universe is not casually riddled with shortcuts. Space doesn't silently collapse into chaos the moment you look away. The same laws that allow exotic possibilities also enforce a kind of cosmic caution. Stability and causality aren't easily sacrificed. Maybe the universe is generous with imagination but strict with construction codes. As the thought settles, your mind softens the images. The roaring collapse quiets into a slow fading, like a campfire burning down to embers. The unstable wormhole becomes less a disappointment and more a guidepost. It points toward the next question. If gravity alone can't hold a bridge open, what else could? Is there some form of matter or energy, something unfamiliar, perhaps that could push space-time outward in the throat, preventing it from pinching off? You'll explore that soon. For now, you hover outside the failed bridge, watching its brief existence as though you're replaying a cosmic time-lapse movie. The throat forms in an instant, then narrows, then vanishes into singularity. No ship passes, no signal crosses, just the stark beauty of geometry revealing its limits. Maybe that's one of the quiet lessons tucked into this part of the story. Not every beautiful idea is also a practical tool, and that's okay. Some structures in nature are meant to be admired rather than used, glimpsed in the equations like rare constellations that you can trace with your eyes but never visit. The early wormholes are like that mathematical fireflies, appearing and vanishing too quickly to touch. You take a slow breath, feeling your chest rise and fall, and let that image fade into the background. The universe, it seems, offers you not just open doors, but also closed ones, and in both cases, there is something to learn. The failure of the first bridges isn't the end of the journey. It's a signpost pointing toward new questions, and toward the strange, exotic ingredients that might be needed to turn a fleeting tunnel into a stable gateway. Maybe, as you drift closer to sleep, you can appreciate the balance. A cosmos whose geometry can dream of wormholes, but whose rules insist that only the most carefully supported ones could ever stay open long enough for a traveler like you. You drift now to the rim of a different kind of question, not, does a wormhole exist? But, What would it take to keep one open? The unstable bridges you've just visited pinch off like frightened sea anemones, collapsing the moment anything tries to pass through. If space-time is a flexible fabric, then wormholes are delicate holes in that fabric, always trying to sew themselves shut. To hold them open, you need something that pushes back. You imagine floating at the entrance of an idealized wormhole, the throat smooth and cylindrical, like a tunnel carved through invisible glass. The air here feels strangely neutral, neither warm nor cold, neither bright nor dark, just a soft, even stillness. Around the throat, instead of rock or metal supports, there is nothing. No beams, no scaffolding, just an invisible condition written into the geometry itself. And yet, the tunnel stays open, refusing to collapse. Something must be doing that work. In ordinary life, you know what holds structures open. Pressure from air inside a balloon, tension in a suspension, bridges, cables, the rigid strength of concrete pillars. In space-time, the equivalent is stress energy, the distribution of mass, momentum, and pressure that appears on the right-hand side of Einstein's field equations. These quantities are usually tame and positive. Mass is positive. Energy density is positive. Pressure may go up or down, but it doesn't usually do anything too strange. Wormholes, though, demand strangeness. To keep a wormhole throat from shrinking, the equations say you need a kind of negative energy density in at least some region. A place where, from a certain observer's perspective, the energy is effectively less than zero. You can think of it like this. Gravity normally pulls things together. Positive energy curves space-time so that paths converge. But a wormhole throat needs space-time to curve the other way, to flare outward instead of inward, like the mouth of a trumpet rather than the neck of a funnel. To get that flaring, you need something that behaves, gravitationally, as if it were repulsive. You might picture yourself inside the throat, gently placing your hand on the invisible air around you. Instead of feeling pulled inward, you have the eerie sensation that space itself is pushing outward, resisting collapse. It's a subtle, disorienting feeling, like standing in a room where up and down briefly trade places. Ordinary matter, atoms, radiation, dust, can't do this job. They always gravitate in the usual way, helping tunnels to collapse rather than holding them open. Physicists talk about energy conditions, simple rules they hoped all reasonable forms of matter would obey. These conditions say, in different technical ways, that energy density, measured by any observer, should be non-negative, that mass and pressure should combine in ways that avoid bizarre behavior. Wormholes that stay open calmly stomp on these rules. To have a traversable throat, the stress energy near it must violate at least some of these energy conditions. In more casual words, you need exotic matter. The phrase sounds like something glowing in a sci-fi engine room, but in physics it mostly means matter or fields whose energy momentum does not behave like anything we normally encounter. It doesn't have to be an entirely new substance. It might be a familiar field in an unfamiliar quantum state. The key is that, averaged in certain ways, the effective energy density is negative. This exotic component must act like a scaffolding made not of steel, but of negative gravitational influence. You breathe slowly as you imagine thin shells of this exotic material lining the throat. They don't shimmer or shine. They're more like regions of reduced presence, pockets where reality is slightly less than usual. The space-time around them responds by curving outward, as if repelled. If you could see gravitational fields as colors, the area might glow in strange shades, cool blues pushing away instead of the usual warm reds pulling in. Is negative energy just fantasy? Here, the story becomes more subtle and perhaps more comforting. In quantum field theory, the framework that describes particles and forces on the smallest scales, the concept of vacuum is not an empty void, but a seething, fluctuating medium. Fields twitch and jitter even in empty space, constantly creating and annihilating virtual particles. In this restless background, there are ways to arrange things so that in some region, for some time, the energy density dips below the usual vacuum level. That's what physicists call negative energy. One of the most famous examples is the Casimir effect. You picture two very flat, uncharged metal plates placed extremely close together, separated by a gap thinner than a human hair by many orders of magnitude. In the darkness between them, something odd happens. Quantum fluctuations of the electromagnetic field are restricted. Not all wavelengths fit comfortably in the gap. Outside the plates, more modes of fluctuation are available. The result is a slight imbalance, a tiny pressure pushing the plates together, as if the vacuum outside is heavier with energy than the vacuum inside. When you describe it carefully, it looks as though there is negative energy density between the plates compared to the outside world. You can almost imagine yourself shrunk down, just in thought. Your body would not thank you for this in reality. Floating in that narrow space between the plates, the vacuum there feels different, as if the quiet hum of quantum fluctuations has been turned down a notch. That lowered hum corresponds to a lower energy density. It's not a dramatic, Hollywood-style glow. It's more like a subtle change in the grain of silence. This gives a hint that negative energy is not purely fictional. Quantum fields can, in fact, arrange themselves in ways that locally violate the classical energy conditions. However, there are important catches. Quantum inequalities constraints derived from quantum field theory limit how much negative energy you can have, how long you can keep it, and how extended in space it can be. It's as if the universe allows you to borrow energy from the bank of reality, but only in small amounts, and only if you pay it back quickly with interest. For wormholes, this is both tantalizing and frustrating. The Morris Thorne picture of a traversable wormhole explicitly assumes the presence of exotic matter threading the throat, providing the necessary negative energy to keep it open. The equations can be satisfied. You can write down a spacetime that is smooth, stable enough for a test traveler, and free of horizons or singularities in the path. But when you ask whether known quantum effects, like those in the Casimir effect, can supply enough negative energy to support such a structure on macroscopic scales, the answers so far lean toward probably not, or at least not without some, as yet, unknown physics. Lying there, you can take that in without needing a final verdict. Your room is quiet, your body heavy, your mind hovering over these strange possibilities. Exotic matter becomes not a promise, but a question mark. Maybe future theories of quantum gravity will reveal new ways for space-time to generate effective negative energy. Maybe exotic matter will remain a purely theoretical ingredient, like a mythical building material in a cosmic architect's handbook. There's a gentle philosophical twist hidden here. To even talk about wormholes as traversable tunnels, we're forced to confront the limits of what we know about matter and energy. The ordinary, comforting stuff around you, air, wood, flesh, fabric, obeys familiar rules that make life stable. Exotic matter, if it exists, would sit at the edge of those rules, testing how far reality can bend before it breaks. You might find it soothing to think that the universe guards its wildest architectures behind layers of difficulty. You can't casually open a gateway between stars. To even contemplate it, you must gather rare, delicate quantum effects or unlock new physics entirely. Maybe that's the cosmos' way of keeping its deeper shortcuts from being overused, like secret mountain paths that only appear under very special conditions. As your eyelids grow a little heavier, you let the image soften. A wormhole throat, quietly lit from within by nothing visible, held open by a halo of exotic matter, negative energy fields whispering outward, defying collapse. You don't need to know exactly how it works, only that our best theories hint it might be possible in principle, while also wrapping it in layers of constraints. Maybe the universe, in its cautious creativity, allows such structures in its rulebook, but makes them painfully hard to realize tiny footnotes in the laws of physics that say, under extremely special circumstances, and with ingredients you probably don't have. You find yourself standing once more at the edge of a wormhole throat, but this time the scene feels different. Before, the tunnels you imagined were like soap bubbles and collapsing bridges, fragile sketches in gravity's notebook. Now, you're stepping into a thought experiment, carefully designed not to crush you. The air around you feels cool and still, like the quiet inside a stone hallway at night. Somewhere in the background, theoretical physicists are murmuring, sharpening their chalk, setting one clear goal: safe passage. You're walking into the kind of wormhole proposed by Michael Morris and Kip Thorne in the late 1980 seconds, not as a blueprint for an actual machine, but as a teaching tool, a way to show students what general relativity can, in principle, permit. They ask a simple, daring question. Can we write down a space-time that is smooth, free of horizons, and gentle enough that an ordinary human, in an ordinary spaceship, could go through the throat without being torn apart? You take a tentative step forward. The floor feels solid beneath your feet, even though you know this is geometry, not stone. In their construction, the wormhole is static and spherically symmetric, unchanging in time, the same in every direction around the center. That calmness is important. A throat that writhes or oscillates would be like a tunnel during an earthquake, dangerous, unpredictable. Here, the walls of space-time are as steady as a held breath. You remember the collapsing Einstein-Rosen bridge and feel a faint apprehension. But this throat has been crafted mathematically to avoid that fate. There is no event horizon here, no point of no return. If you shine a flashlight behind you, light can still escape back to where you started. If you change your mind halfway through the journey, you can, at least in the equations, turn around and go home. That alone makes this wormhole feel kinder, less like a trap, and more like an experimental hallway. The key to your comfort is the way the curvature is arranged. The metric, the function that tells you how distances and times are measured, is chosen so that the throat has a minimum radius, a gentle bottleneck rather than a razor's edge. Imagine walking through a long, cylindrical tunnel whose walls never close in further than, say, a few tens of meters around you. You're not being squeezed into a needle, you're strolling down a cosmic subway. You press your palm against the wall of the throat in your imagination. You don't feel bricks, but you sense something else, the presence of exotic matter you met in the last section. It doesn't glow or hum, it reveals itself only by what it does to space-time. Near the throat, gravity doesn't focus paths inward as usual. Instead, the geometry flares out, like the lip of a trumpet, ensuring that the tunnel doesn't pinch closed. That flaring is encoded in what relativists call the shape function. You don't need the formula, you just need the feeling. The walls curve outward, not inward. Morris and Thorne put constraints on this geometry with you, the traveller, explicitly in mind. They imagine a ship crossing from one mouth to the other, with people inside who would like to arrive in one piece. That means tidal forces, those differential pulls that stretch and squeeze, must remain small. The difference in gravitational pull between your head and your feet should not exceed what you experience on Earth. In practice, that translates to bounds on how quickly space-time can curve over your body's length. You picture yourself floating inside a small cabin. Outside the windows, the view of the universe warps in slow, deliberate ways, stars sliding, blues and reds shifting. But inside, your stomach feels calm. No wild lurching, no sense of falling into an abyss. Your internal organs aren't being tugged in different directions. The designers of this theoretical wormhole have tuned the curvature so that, locally, you feel at most mild accelerations, the kind a roller coaster engineer would classify as gentle. Time is another concern. A traversable wormhole is only really interesting if you can cross it in reasonable time, measured by your own clock. The Morris Thorne scenario imagines distances and travel speeds such that you could, in principle, go from one mouth to the other in hours or days, not geological eras. You can almost hear the quiet tick of a wristwatch as you drift down the throat, knowing that on the other side, another region of space waits at a distance that, through ordinary space, would have taken centuries of flight. You might notice how domestic this begins to feel. The wildest structure in space-time is being talked about in terms of seatbelts, comfort, acceleration, limits human-scale needs. It's like designing a mountain tunnel with not only engineers and physicists, but also passengers and their coffee cups in mind. The mathematics, dense and forbidding on the page, are here in service of a simple question. Can an ordinary person, in principle, get through this without being destroyed? Of course, beneath this gentle corridor lies the same requirement as before: exotic matter. The stress-energy tensor that supports this geometry is not that of dust or gas or light. In certain regions, when measured in specific ways, the energy density must be negative. The wormhole throat is like a carefully balanced compromise between stability and transgression. Steady in its shape, yet violating classical energy conditions that once seemed almost sacred. You might think of it as walking through a building whose beams are made of a material you don't yet know how to manufacture. The architects can describe its properties. They can say it must push rather than pull, must resist, collapse in unusual ways, must exist in just the right arrangement. They can check, on paper, that if such beams existed, the structure would stand. But no one has yet found a way to forge the beams in reality. As you move along the tunnel in your mind, the view through the far mouth begins to change. Perhaps you started near Earth, with familiar constellations outside one entrance. As you emerge from the other mouth, the sky could be wildly different, the Milky Way seen from another arm, another galaxy altogether, or simply a distant part of your own neighborhood, shifted by tens or hundreds of light years. The journey felt like a single, continuous walk. The distance you've skipped over is encoded not in your muscles, but in the geometry you pass through. There's a quiet, reflective comfort in that. You realize that far and near are not absolute. They are stories we tell based on the paths we're allowed to take. On a flat map, two towns, separated by a mountain, are far, but a tunnel changes the story. On the cosmic map, stars and galaxies feel impossibly distant, but a wormhole would redraw the legend, giving you new notions of neighborhood and next door. Still, your mind knows this is all within the realm of in-principle. No one has built such a tunnel. No one has measured exotic matter scaffolding a throat. The Morris Thorne wormhole is a proof of concept, more like an artist's rendering than a construction schedule. It tells you that general relativity, when combined with certain stress-energy distributions, does not forbid safe passage. It leaves all the hard questions. Can exotic matter exist in sufficient amounts? Can it be arranged stably? To future work? You might find that strangely soothing. The universe you're trying to fall asleep in is not one where shortcuts come cheaply. Safe passage, even in thought experiments, demands careful tuning, delicate ingredients, and a respect for the complex ways space-time responds to matter. Maybe the cosmos is whispering. Yes, extraordinary paths might exist, but only where the rules are honored in deeper, subtler ways. As your body sinks a little heavier into the bed, you can let the images blur. A smooth, cylindrical throat illuminated by distant starlight. A ship drifting through with its crew calm and uncrushed. Exotic matter, silently shaping the corridor. Two mouths opening onto distant skies. Maybe the universe just loves to tuck possibilities like this into the folds of its laws, a reminder that impossible is sometimes just not yet understood. And that safe passage, if it ever comes, will be as much about patience and insight as about power. You're still standing inside that calmly lit wormhole throat when someone, somewhere in the control room of this thought experiment, has a new idea. Up to now, you've used the tunnel as a shortcut in space. One mouth here, the other far away, connected through this gentle corridor in between. But space-time is not just space. Time is woven into every curve. If you can drag one mouth through time in a different way than the other, the wormhole stops being only a bridge in distance. It starts to become a kind of clock, and maybe a time machine. You take a slow breath and imagine the two mouths of the wormhole. Mouth A, floating near Earth in a quiet orbit, bathed in familiar starlight. Mouth B, attached to a sturdy ship, sleek, silver, humming softly, ready for a relativistic journey. At the beginning, the clocks at both mouths are synchronized. If you peered through the tunnel from one side to the other, you'd see the same time on both sets of dials, the same steady ticking, as if they were sitting side by side. Now the journey begins. Mouth B's ship fires its engines. You don't hear the roar in the vacuum, but you can feel the idea of acceleration, a gentle pressure pushing you into your seat as the ship's hull warms just a little, vibrating with power. In this thought experiment, the ship goes out at a significant fraction of the speed of light, coasting through the dark. From your perspective, back near Mouth A, years might pass. Stars drift slowly. The ship becomes a faint, stubborn point of light against the black. But from the perspective of the crew with Mouth B, time moves differently. According to special relativity, clocks on fast-moving objects tick more slowly compared to clocks at rest. Their hearts beat at a normal pace to them. Their days feel ordinary, but when they look at a distant reference clock, they know it's racing ahead. Time dilation is not just a concept. It's something we've measured in high-speed particles and in atomic clocks flown on airplanes. It's a real, if usually tiny, bending of time. You picture two wristwatches at launch. One stays with Mouth A, the other rides with Mouth B. The ship spends a long stretch at high speed, then turns around and comes back to reunite with its twin. This is the classic twin paradox, but with a twist. One twin now brings back an entire wormhole mouth as luggage. When the ship returns, and mouths A and B are once again near each other in ordinary space, their clocks no longer agree. The watch that stayed with A shows, say, 100 years having passed. The watch that travelled with B might show only 20. The ship's crew is younger, their time stretched out less. To you, standing near A, mouth B feels like it has travelled into the future relative to its sibling. You step closer to mouth B, feeling the faint warmth of its hull radiating into the vacuum. The ship's metal cooled from its journey, but still echoing with the memory of motion. The two mouths now sit side by side in space. If you walk from A to B the long way through normal space, they share the same here and now. But inside the wormhole, something different has been happening. The tunnel has been quietly remembering its own proper times at each end. Inside the wormhole, the geometry has kept as proper time linked to B's, but each end has aged according to its own experience of space-time. From the perspective of the tunnel, one mouth's clock is far ahead of the other. So when you step into mouth A and stroll through the throat, you're walking along a path that lines up equal proper times. You emerge from mouth B not at the same external time you just left, but at the internal time matched by the wormhole's history. If mouth B's clock lags behind, then going from A to B through the wormhole is like stepping into a corridor and emerging in the past relative to outside world. You can feel the strangeness of that as a chill along your spine. You leave A on, say, the 1st of January 2300, walk a short distance through the tunnel, and step out of B on a day that, in the outside universe, corresponds to January 1, 2220. On the other hand, going from B to A would be like jumping into the future. The wormhole has become a two-way time offset, a cosmic clock skewed between its ends. You stand in the middle of the throat, halfway between the mouths, and let the implications wash over you. Time, which in everyday life trudges forward at a stubborn, uniform pace, has here become something you can loop around. You imagine the gentle ticking of clocks at each mouth, slightly out of sync, the difference fixed by the journey mouth B took. The wormhole is no longer just a bridge between distant places, but a bridge between different nows. You might picture an old-fashioned train station with two platforms and two enormous clocks. One reads 10, the other 9. A short hallway connects the platforms. In normal architecture, that's impossible. Both platforms share the same present. But in space-time architecture, the wormhole makes that short hallway link moments separated by decades. You can step from late morning to early morning with a few steps, like slipping through a crack in the day. Of course, your sleepy mind might begin to whisper, "Isn't this a time machine?" And the theory answers, softly, in principle, yes. If you can create such a time shift between the mouths, and if you can move freely through the wormhole and then return by normal space, you could, in principle, send information, or even objects, into the past of the external universe. The geometry doesn't forbid it outright. It simply asks that exotic matter hold the throat open and that relativity's rules about time dilation and acceleration be followed. You feel the tension between wonder and unease. On one hand, it's mesmerizing, time travel arising not from magic spells or paradoxical gadgets, but from the same laws that govern GPS satellites and particle accelerators, just applied on a grander, more imaginative scale. On the other hand, you can sense trouble brewing. If signals can loop back and influence their own origin, if cause and effect can bend back on themselves, can the universe stay logically consistent? For the moment, you simply let yourself feel the softness of the idea, without wrestling it to the ground. The wormhole as a cosmic clock is like a pair of intertwined watches, each aging at its own pace, connected by an internal passage that refuses to forget their shared history. The different flows of time on each side create a standing time difference, like a river that splits around an island and then rejoins with one branch having taken a longer, slower route. You might look down at your own hands in the dim tunnel light and consider how intimately you live with time already. Your heartbeat, your breathing, your rhythms of sleep and waking, all of them are tiny clocks. You feel time as warmth on your skin at midday and coolness at night as the gradual dimming of the day's noise into the hush of evening. You are already a traveller through time, moving 1 second per second into your own future. Here, the wormhole invites you to imagine a different relationship, one where you could sidestep the steady march, where distance and duration can be traded in surprising ways. Maybe the universe in the pure logic of its equations, allows this. Maybe it also hides subtle protections that prevent paradoxes, nudging events so that self-contradictions never quite happen. Those questions, the paradoxes, and possible protections belong to the next bend in our journey. For now, as you settle a little deeper into your pillow, you can let the image of the cosmic clock linger. 2 mouths, 2 mismatched times, 1 tunnel, stitching them together. A quiet machinery of space-time that suggests, with a mix of daring and caution, that shortcuts through space might also be shortcuts through time. Maybe the universe just loves to show that the boundaries you think are solid here versus there, now versus then, are, under the surface, woven from the same continuous fabric, waiting for the right geometry to fold them together. You stand now at the edge of a very strange possibility. A wormhole that doesn't just cheat distance, but also plays tricks with time. One mouth ages differently from the other, and suddenly the tunnel between them looks suspiciously like a time machine. As you hover near one entrance, the air around you feels still, almost expectant, like a theatre just before the curtains rise. Behind the quiet, there's a big question humming. If you can go backward in time, what happens to cause and effect? You let a simple story form in your mind. Suppose mouth A is in your present. Mouth B has been dragged around and time shifted so that, from the perspective of the outside universe, it sits in your past. If you step through from A to B, you emerge earlier than when you left. Now, imagine sending a message, "Don't build the wormhole." If that message arrives in time, maybe the wormhole never gets completed, which means you never had a way to send the message in the first place. Your thoughts trace out a loop, and you can feel the logical tension like a knot in your stomach. This is the kind of scenario people call a time travel paradox. The most famous version is the grandfather paradox. Someone goes back in time and prevents their grandparent from ever having children, thereby preventing their own birth, which means they couldn't have gone back to interfere. It's a little gruesome, so you might soften it in your mind. Maybe you go back and stop your younger self from making a decision that led you to the wormhole project. If you succeed, you never discover the tunnel, never travel, never return to interfere. The story keeps eating its own tail. You picture this as a shimmering loop of light in front of you. A beam leaves one point, travels through the wormhole, comes out earlier, and then somehow blocks its own departure. Underneath the pretty glow, the logic breaks. The universe seems to be forced into a contradiction. Event A both happens and doesn't happen. You can almost see the space-time diagram, lines curving and folding until one path crosses back into its own origin. Physicists refer to this kind of structure as a closed, time-like curve, a path through space-time that always moves forward in local time, but loops back to where it started in the global picture. If traversable wormholes can be turned into time machines, they can generate these loops. That's both fascinating and deeply troubling. We're used to a world where causes come before effects, where you can't receive a reply to an email you haven't sent yet, where broken cups don't reassemble themselves on the floor. You listen to the quiet around you, the small, random sounds of your own environment, and notice how strongly your everyday intuition leans on that one-way arrow. You wake, you live, you sleep. Memories accumulate in one direction. Old photographs show younger versions of you, never the other way around. The idea that space-time itself might allow loops where an event can influence its own cause feels like walking into a mirror maze where every reflection claims to be the original. Some scientists have tried to handle this by suggesting consistency constraints. The idea that, even if closed time-like curves exist, the universe only allows self-consistent histories. In this view, if you go back and try to change the past, you always end up doing something that was already part of the past you remember. You slip on the steps, the gun jams, your warning is misunderstood. No matter what you attempt, the timeline closes itself without contradiction. The paradox dissolves, not because time travel is forbidden, but because outcomes that would create logical loops are simply never realized. You can think of it like a river that might swirl and loop in eddies, but never crosses itself in a way that makes water flow both upstream and downstream at the same point. Locally, the flow can be complex. Globally, it's still consistent. It's a subtle, almost mystical-sounding idea, but it stays within the logic of physics. The equations don't care about your feelings of free will. They only care that the boundary conditions yield solutions without contradictions. Still, not everyone is satisfied with that picture. Another line of thought, associated most famously with Stephen Hawking, carries a different whisper. Maybe the universe has a built-in safety feature. Maybe whenever conditions arise that would allow the creation of closed time-like curves, a wormhole tuned into a time machine. For example, quantum effects spool up, fluctuations grow, and the structure destabilizes. This idea has a name that sounds almost like a science fiction book title: the chronology protection conjecture. You imagine standing near the mouth of a wormhole as engineers start to move one end around to create a time shift. At first, everything is calm. The tunnel is stable. The exotic matter holds the throat open. Clocks tick along. But as the geometry twists toward allowing a loop in time, something odd begins to happen. Quantum fields that were humming quietly in the background start to roar. Virtual particles, those brief, flickering disturbances in the vacuum, see an opportunity. In the presence of a would-be time machine, the paths that particles can take become tangled. Some paths might loop back on themselves, creating multiple opportunities for constructive interference. Certain modes of the field may get amplified again and again, like sound feeding back in a microphone loop. What was once a gentle whisper of quantum fluctuations grows into a scream of energy density. You can picture it like standing in a still room, then slowly moving a microphone closer to a speaker. At first, everything is fine. Then you hit a certain configuration, and suddenly an awful squeal fills the room, overwhelming everything else. In a similar way, the quantum fields near the formation of closed time-like curves might blow up, with energy densities increasing without bound as the geometry approaches the dangerous configuration. If that happens, the very energy needed to form the time machine could back-react on space-time, warping it in such a way that the problematic region never fully develops. The would-be time loops are blocked by their own consequences. You might picture the wormhole's throat trembling, then collapsing, like a tunnel whose walls begin to shake and crumble, just as workers try to carve a forbidden passage. From your sleepy vantage point, you don't need every technical detail. It's enough to know that, as far as we've been able to probe the theory, the combination of general relativity and quantum field theory seems hostile to the casual creation of time machines. Traversable wormholes might exist in equations, and they might, if manipulated cleverly, threaten to create closed time-like curves. But when you add the effects of quantum fields, the universe appears to push back, piling up stress energy precisely where it's needed to shut the door. You feel a quiet relief in that. It suggests that while the cosmos may allow wild speculations in its mathematics, it also guards the basic flow of cause and effect with hidden feedback loops. The arrow of time you trust when you pour a cup of tea or send a message to a friend isn't easily broken by clever engineering. The logical fabric of reality resists being folded into contradictions. Of course, none of this is a final, proven theorem. Chronology protection is a conjecture, a strong suspicion based on the best tools we have. Some researchers continue to explore alternative models where time travel of certain restricted kinds might be allowed. Others search for a deeper theory of quantum gravity that could settle the question. For now, the picture is unresolved, but leaning toward a universe that prefers consistent histories over paradoxical ones. As you lie there, feeling your body grow heavier and your thoughts a little softer around the edges, you can let this uncertainty be gentle rather than disturbing. Maybe the universe is structured like a good story, rich in twists, full of unexpected turns, but ultimately coherent, never letting the plot truly contradict itself. Wormholes and time loops become, in this view, tools that theories can play with, while reality itself maintains an underlying narrative logic. You might even find it comforting to think that if wormholes ever do exist in a usable form, they'll be bound by these deeper protections. No changing your past, no erasing your own experiences. At most, perhaps, you'd get new ways to connect with distant places and times, within a framework that still respects the quiet rule you live by every day. What's done is done. Maybe the universe just loves to flirt with impossibilities in equations, while keeping the actual world you inhabit delicately stable, letting you drift towards sleep, wrapped in a reality where tomorrow comes after today, and where even the wildest tunnels through space-time can't untie the basic knot of cause and effect. After all the stretching and folding of cosmic tunnels, You begin to drift downward, as if your mind is riding an elevator from the vast architecture of galaxies to the tiny, restless world of particles. The air in your imagination cools and darkens, and the stars outside your window dissolve into a fine mist. You're entering the quantum realm now, where things don't behave like little billiard balls, but like overlapping possibilities, humming softly with uncertainty. Here, instead of wormholes you could almost fly a ship through, you meet something much smaller and stranger: entanglement. You picture two particles born together in some microscopic event, maybe a decay, maybe a collision in a lab. They rush apart, racing away into the darkness. One might end up near you, the other might drift light years away, yet somehow they remain linked, like two notes of a chord that never quite stop resonating with each other. You imagine them as tiny glowing specks, one blue, one red, draped in a faint thread of silver light. That silver thread doesn't exist in space the way a string does. It's more like a connection in the book of possibilities, a shared quantum state. When you measure one particle, asking it a simple question about some property, the outcome is correlated with what you'd find if you measured the other, no matter how far apart they have traveled. It's as if the universe insists that the two results fit together into one complete pattern. Einstein once called this spooky action at a distance, because it seems, at first glance, to imply some faster-than-light influence. But careful experiments have shown again and again that entanglement is real. You can't use it to send messages faster than light. Nature is still strict about that. But it tells you that the quantum world doesn't fit neatly into our classical intuition of separate, independent objects. Instead, systems can be deeply, inseparably connected in their underlying description. You let that sink in while you feel the texture of your pillow or the softness of your blanket. Just as the fabric under your hand is woven from threads, the quantum state of the universe might be woven from entanglement. If you could see it, you might find that every region of space is bound to others by invisible correlations, a vast web of relationships that define not just what things are, but how they are allowed to be together. Now, gently, you bring back that earlier image of a wormhole, a bridge in spacetime connecting distant regions. Somewhere in the overlap between gravity and quantum theory, a bold conjecture appears, like a handwritten note in the margin of the equations. ER equals EPR. The letters stand for two different ideas. ER refers to Einstein, Rosen bridges, those wormhole solutions we met earlier. EPR refers to Einstein, Podolsky, and Rosen, whose famous thought experiment on entanglement challenged the completeness of quantum mechanics. The conjecture suggests that these two seemingly separate concepts might be deeply connected, that entangled particles are, in some sense, linked by tiny quantum wormholes. You picture again your pair of entangled particles, blue and red, drifting apart. Now, in your mind's eye, you zoom into the space between them and imagine a microscopic, shimmering tunnel connecting them far too small for anything to travel through, more of a metaphorical bridge than a passageway, but a bridge nonetheless. The idea is not that you can send a spaceship along this thread, or even a single photon. It's that the same mathematics that describes entanglement might also be interpretable as a kind of wormhole geometry in a deeper theory of space-time. In certain models of quantum gravity, especially those inspired by the holographic principle and string theory, people have found concrete examples where a pair of strongly entangled systems corresponds, on the gravity side, to two regions of spacetime connected by a wormhole. From the outside, the systems just look like entangled quantum states. From another perspective, in a dual description, you see a geometric bridge. It's as if reality offers two languages for the same relationship, one in terms of information and correlation, the other in terms of shape and distance. You might imagine a book printed in two columns. On the left, the story is written in the language of quantum bits, entanglement, entropy, and unitary evolution. On the right, the same story unfolds in the language of curvature, horizons, and tunnels. ER equals EPR is the suggestion that the lines match, that whenever you see strong entanglement on the left, there is some corresponding, perhaps highly quantum, wormhole-like structure on the right. As you lie there, eyes maybe half closed, you can let this idea feel less like a technical conjecture and more like a gentle metaphor. Entanglement is the thread that stitches space-time together. If that's true, even approximately, even in some specific models, then wormholes stop being an exotic add-on and start feeling like a natural expression of quantum connectivity. The vast, smooth geometry you floated through earlier might, at its deepest level, be woven from countless tiny bonds of entanglement, like a tapestry woven from threads you can't see individually. You imagine taking away entanglement, unweaving those invisible threads one by one. Perhaps space-time would begin to fray, its smooth structure breaking into disconnected pieces. In some theoretical explorations, reducing entanglement between regions really does make the distance between them blow up in the geometric description. It's as if entanglement doesn't just live in space-time, it helps define what near and far mean in the first place. There's something quietly moving about that. The same mysterious quantum links that let particles share a joint state might also underlie the very continuity of the universe you float in. The cosmos, which from your pillow looks like a serene, continuous expanse of stars, may be secretly upheld by an intricate web of correlations, each one a tiny promise that this part of reality is connected to that part in a precise, lawful way. Of course, ER equals EPR is still a conjecture, a proposal in the evolving dialogue between quantum theory and gravity. It's not a finished, polished theory you can write on a postcard, but as you drift towards sleep, you don't need it to be. You just let yourself rest in the possibility that the universe might be more unified than it appears, that the tunnels of curved space-time and the threads of quantum entanglement are two sides of the same quiet mystery. You can weigh that mystery gently in your mind, the way you might weigh a smooth stone in your hand, feeling its coolness, its rounded edges, without needing to know exactly where it came from. Maybe, at every scale, from galaxies down to electrons, connection is more fundamental than separation. Maybe what you think of as empty space is actually the most densely woven thing of all, full of quantum links and subtle bridges. And when you think about your own life, all its relationships and memories, you might notice a soft echo. Just as particles can be entangled, so can experiences and people. A song heard long ago can still stir your chest. A friend far away can live vividly in your thoughts. These are not quantum phenomena, but they rhyme with the idea that distance is not the whole story, that what matters is how things are linked. Maybe the universe just loves to reuse patterns, threads and tunnels, bonds and bridges, from the smallest scales of entanglement all the way up to wormholes between stars. And as you breathe slowly in the dark, those patterns can feel a little less intimidating and a little more like a lullaby of the cosmos, whispering that, beneath all the empty space, everything is quietly, deeply connected. You rise up again from the quantum haze, back into the vastness between stars, and you find yourself in a control room that doesn't quite exist, at least, not yet. It's quiet here, dimly lit by soft panels that glow with deep blues and purples, like a midnight ocean turned into circuitry. Outside, an enormous window stretches a galaxy-sprinkled darkness. This is the imagined heart of a far future civilization, one advanced enough to even ask the question, could we build a wormhole? You stand in the center of the room, feeling the floor steady beneath your feet, and let the engineers of this civilization gather around you in your mind. They aren't human, necessarily. They might have different shapes, different senses, but they share one thing with you: curiosity. They've learned general relativity long ago, mastered quantum field theory, measured black holes and neutron stars the way we measure mountains and rivers. For them, gravity is not just background, it's a tool. On a vast display in front of you, they show the plan. Two regions of space, unimaginably far apart, are marked like distant cities on a map. Point A, in one arm of a spiral galaxy. Point B, near the edge of a globular cluster. Between them, on the map, someone draws a simple arch, just a line, representing the desired wormhole. But the engineers all know that innocent line hides terrifying numbers. You watch as they start listing the requirements. First comes the mass energy budget. Even if they manage to keep the wormhole throat only a few hundred meters wide, just enough for ships and cargo, the amount of exotic matter needed could be enormous. Calculations from our own physics, extrapolated wildly, suggest energy densities far beyond anything humanity can currently generate. You imagine a power plant the size of a star, its output diverted and reshaped into negative energy configurations, just to hold open a single stable tunnel. In your mind, you feel a gentle pressure at your temples, as if the sheer scale of those numbers is pushing there. The engineers around you speak in calm, measured tones, but the graphs on their displays climb almost straight up, like cliffs. They must gather not just energy, but control over energy down to quantum details, arranging fields in delicate patterns that sustain negative energy densities without blowing up into chaos. They consider where to place the mouths. One option: build the wormhole small and then slowly inflate the throat, feeding it with exotic matter like a balloon, while moving the mouths apart at sublight speeds. You see a mental time-lapse. A tiny, microscopic tunnel, coaxed open molecule by molecule, meter by meter, until it reaches human scale and beyond. Along the way, tidal forces must be kept small, quantum instabilities suppressed, and any stray ordinary matter carefully shepherded so it doesn't collapse the structure. Another option: form each mouth near massive objects that they already know how to manipulate. Perhaps black holes they've tamed with vast orbiting structures, using their gravity wells as anchors. But that introduces new hazards: tidal forces, time dilation, intense radiation. The engineers debate, moving markers on the holographic map, balancing convenience against survivability. It's cosmic urban planning, with wormholes as interstellar subway lines. You walk closer to the imagined wormhole generator, a ring of structures surrounding where the throat will form. Maybe they look like immense, concentric halos of superconducting coils, or arrays of lasers, or something beyond our current imagination. A forest of devices shaping quantum fields directly. Around the central region, space feels oddly hollow, as if the usual sense of distance has gone thin. The air, or whatever medium they use, hums with barely contained power. At the very heart, space-time begins to deform. You picture a faint distortion appearing, like a mirage in hot air. Lines that once ran straight begin to bend toward a point that isn't exactly a point. The engineers adjust parameters, dialing up negative energy here, adjusting curvature there, keeping 1,000 constraints satisfied. They must respect not only Einstein's equations, but also quantum inequalities, stability conditions, and whatever deeper laws their more complete theory of quantum gravity demands. You can feel just how precarious it all is. It's like trying to build a tunnel through an active volcano using ice and spider silk, while earthquakes rattle the ground. Any misstep and the geometry could snap back, releasing catastrophic bursts of energy, or producing a black hole instead of a smooth throat, a lethal mistake. The control room is quiet, but the challenge is deafening. Then there's the question of communication and synchronization. To use a wormhole for travel or transport, both mouths must be managed. If they drift into hazardous environments near supernovae, inside dense gas clouds, or through regions of wild gravitational waves, the entire structure may be stressed. So our imagined civilization builds huge stabilization arrays around each mouth, swarms of satellites monitoring curvature, adjusting field generators, compensating for tidal perturbations. You might imagine this as gardeners tending a very temperamental tree whose roots are buried not in soil, but in the fabric of reality. They prune and support, constantly measuring, constantly adjusting. The wormhole isn't just built once and left alone. It's maintained, like a bridge that must be inspected daily because the universe is always pushing, pulling, flexing around it. From your quiet, earthly vantage point, this level of engineering is almost comical in its scale. Humanity has only just begun to detect tiny ripples in space-time gravitational waves from distant black hole mergers. Our biggest machines sit on or near a single small planet. We fumble to confine plasmas, to align mirrors, to keep quantum states coherent for fractions of a second. In that context, the thought of engineering a macroscopic wormhole feels less like a roadmap and more like a meditation on how far the concept of technology might stretch. But there's something soft and inspiring here too. By imagining such a project, you get a sense of how deeply a civilization would have to understand the laws of nature, not just formulas, but the full, detailed interplay of gravity and quantum fields. They would need to harness energies approaching those of stars, yet shape them with the delicacy of a watchmaker adjusting springs. They would have to earn their shortcuts by mastering the long path first. You glance around the imaginary control room and notice that, despite their power, these beings still check and recheck their numbers. They still worry about instabilities, paradoxes, and the unknown. Even at this far edge of possibility, humility is part of the engineering process. The universe is vast and subtle, and any attempt to create a stable, traversable wormhole is a negotiation with its deepest rules. In your own life, that might translate into a quiet lesson. Some doors only open after a long apprenticeship. You can't jump straight to wormholes, any more than you can jump straight from a matchstick to a star. Progress is incremental. Each new understanding builds on countless smaller insights and experiments, just as any future wormhole builders would have spent millennia studying black holes, quantum fields, and spacetime itself. There's another, more philosophical question floating in the air. Even if a civilization could do this, should it? A network of wormholes would reshape not only travel, but power, culture, and risk. Instantaneous connections across galactic distances could spread knowledge and conflict at unprecedented speeds. Tunnels might destabilize natural structures or become targets in wars between very patient beings. Cosmic engineering is not just about technical ability, it's about responsibility. You let that thought drift as softly as you're breathing. Right now, for you, wormhole construction is safely confined to dreams and equations. Your bed is your starship. Your ceiling is your night sky. The fact that our best theories even allow us to write down such projects says something beautiful about the universe. It is rich enough, flexible enough, that its laws can be stretched in imagination far beyond what we can build. Maybe no civilization ever reaches this level. Maybe the constraints of negative energy, quantum instability, and sheer scale prove insurmountable. Or maybe, somewhere in the deep future, under alien stars, someone does manage it. A single, tenuous bridge between two remote points, tended carefully like a sacred fire. As you lie there, caught between wakefulness and sleep, you don't need to choose. You just let the possibility exist as a kind of cosmic lullaby. The thought that the same quiet equations that govern falling apples and orbiting moons also whisper about tunnels through space-time. Whether or not anyone ever builds them, those whispers are part of the universe's story. Maybe the universe just loves to leave these possibilities scattered in the margins of its laws, like invitations reminders that there is always more to learn, and that even the wildest technologies begin as someone, somewhere, closing their eyes and asking, very softly, what if? You leave the gleaming control room of that far future civilization behind and drift back into a quieter, older universe. The one that exists whether or not anyone tries to engineer it. Out here, between galaxies and clusters, the darkness feels ancient and patient. Stars burn, collide, and die without asking your permission. Black holes grow fat on gas and starlight. Gravity sculpts everything over billions of years. And in this slow, relentless workshop, a question follows you like a soft echo. Could wormholes form on their own? You imagine yourself floating far from any planet, wrapped in the cool silence of intergalactic space. The nearest galaxies are faint smudges, like breath on a window. There are no engines here, no exotic laboratories, just the raw ingredients of the cosmos. Matter, radiation, dark matter, dark energy, quantum fields, all humming along, according to the same laws that shaped the early universe. If wormholes can occur naturally, this is the sort of place that have to emerge from not out of ambition, but out of sheer inevitability. Your mind goes back to the very beginning. The first fractions of a second after the Big Bang, temperatures indescribably high, densities beyond anything your body can really feel. If you try to imagine it, it's like stuffing all the warmth of a million suns into the palm of your hand until it's too bright to see, too intense to think about. In some speculative scenarios, quantum fluctuations of space-time itself could have been wild during that time. Peaks and valleys in the geometry bubbling in and out, forming tiny, transient tunnels. These would be quantum foam wormholes, tiny beyond comprehension, appearing and vanishing at scales vastly smaller than atoms. They'd be like momentary pores in the fabric of space-time, flickers in a deep, seething sea. You can picture them as miniature tunnels winking into existence and then collapsing almost instantly, too brief and too small for any particle, let alone a traveller, to use. Still, the idea that space-time at its most fundamental might be pocked with fleeting wormholes gives a sense that the universe itself is experimenting, tossing up possibilities and letting most of them fade. You breathe slowly and imagine that foam settling as the universe expands and cools. Structures form. First tiny density fluctuations, then gas clouds, stars, galaxies, clusters. Gravity takes over as the dominant sculptor of large-scale reality. If natural, macroscopic wormholes exist, they would have to survive this violent adolescence of the cosmos supernovae, black hole mergers, tidal shredding near dense objects. The question becomes, can any of those microscopic quirks be stretched and stabilized by cosmic evolution into something large and durable? Most studies suggest the answer is probably no, at least not with the kinds of matter and energy we typically see. The same stability issues that plague engineered wormholes apply to natural ones. Ordinary matter tends to make throats collapse, not stay open. To have a macroscopic, long-lived wormhole, you still seem to need exotic matter or effects that violate the usual energy conditions. The universe, on its own, overwhelmingly prefers positive energy densities. Stars, gas, dust, dark matter, clumps things that gravitate in the familiar way. You might picture yourself drifting near a galaxy cluster, watching arcs of light curve around massive regions as gravitational lenses. These distortions are real and observed. They are spacetime bending under the weight of matter. If there were a wormhole here, one of the ways you might hope to spot it is through how it bends light, a lensing pattern different from what a normal mass distribution would create. People have actually looked for such strange signatures, scanning sky surveys for objects whose gravitational pull doesn't match their visible structure. So far, the sky has been quiet on that front. We see black holes, neutron stars, galaxies, and the familiar zoo of gravitational lenses, but no clear sign of a mouth that leads somewhere else entirely. If natural wormholes exist, they are either extremely rare, extremely well hidden, or so small that their effects blend into the background noise of the universe's chaos. You let that thought sink in as you feel the real-world weight of your blanket anchoring you. The cosmos outside is not a chaotic carnival of random tunnels. It is, on large scales, surprisingly smooth and predictable. Galaxies follow patterns. Cosmic microwave background radiation spreads out almost uniformly, with tiny ripples. The universe behaves more like a calm ocean with gentle swells than like a storm full of spontaneous whirlpools. Still, the possibility lingers. General relativity allows solutions describing wormholes. Quantum field theory hints at negative energy densities in special situations, and there are speculative models, often involving dark energy or modifications to gravity, where wormhole-like structures might, in principle, arise as part of cosmic evolution. In some of these, what we call dark energy or certain scalar fields could, if arranged just right, support a throat. It's highly conjectural, but it keeps the door slightly ajar. You might imagine a region where the usual gravitational tug-of-war behaves strangely. Instead of everything wanting to clump more tightly, some field configuration pushes back just enough to keep a tunnel open. In your mind's eye, you see a pair of mouths embedded in the cosmic web, the great filaments of galaxies that stretch across hundreds of millions of light-years. They'd look, from far away, like odd halos or peculiar mass concentrations, perhaps with unusual relationships between the light they bend and the matter we can infer. But even if such entities exist, remember how unforgiving the environment can be. Streams of gas, galaxies in motion, gravitational waves from distant collisions, all of these could perturb a delicate wormhole throat. Without continuous maintenance from some underlying field or mechanism, the tunnel would likely collapse long before any curious traveler finds it. You may find a kind of quiet reassurance in that. It suggests that your universe isn't randomly riddled with traps and shortcuts. The rules that allow stars to shine and planets to orbit also make large, stable, naturally occurring wormholes improbable. The everyday reliability of cause and effect, the fact that you can set your alarm and trust that morning will come in an orderly way, is tied to the same structures that make wild features like wormholes hard to realize. From your pillow, under your particular patch of sky, you can imagine astronomers scanning with big telescopes, looking for oddities, stars orbiting invisible companions in strange ways, lensing events that don't match normal models, flickers in gravitational wave signals that might hint at structures more exotic than black holes. So far, every strange signal has turned out to have more mundane explanations. But the search continues, not because we expect wormholes to be common, but because the universe has surprised us before. Maybe that's the soft balance here. Scientifically, natural, macroscopic wormholes seem unlikely under known physics and observations. But the fact that the equations allow them, and that we can at least imagine conditions under which they might exist, keeps a small ember of possibility glowing. You don't need the sky to be full of gateways for it to be wondrous. It's enough to know that the laws we've uncovered are spacious enough to include such wild geometries, even if the cosmos rarely, if ever, chooses to realize them. As your eyes grow heavier, you might think of the universe as a careful architect. It prefers structures that are stable, reproducible: stars, planets, galaxies, black holes. If it builds wormholes at all, it may do so only in the tiniest ways, in quantum foam flickers, or in rare, delicate configurations we haven't yet recognized. The night above you is mostly continuous, mostly predictable, and within that continuity, human beings have already found so much to marvel at. Maybe the universe just loves to leave a few extreme possibilities at the edge of its design space, natural wormholes among them, not as everyday scenery, but as hints. Hints that even when the sky looks calm and familiar, there are still corners of the cosmic rulebook we don't fully understand, still reasons to keep looking up, still room for wonder as you drift gently towards sleep. You're still floating in that wide, patient universe, carrying the quiet question of natural wormholes with you, when another, more practical thought arrives. Even if a wormhole did exist out there, natural or engineered, how would anyone ever know? You can't just look up and see a glowing portal conveniently labelled "shortcut this way." Wormholes, if real, would be subtle, buried in the fabric of space-time itself. To find one, you'd have to listen to the universe very carefully. So you imagine yourself back at Earth, standing in a darkened control room at a big observatory. Banks of screens glow softly, showing star fields, curves of data, little spikes and dips that mean something to the scientists half whispering around you. Outside, the night is clear, the air cool against the windows. Above you, telescopes turn with slow, deliberate motion, like giant, sleepy eyes tracking invisible prey. The first trick astronomers reach for is an old friend: gravity as a lens. Massive objects bend light, and wormholes, being made of curved space-time, should too. You picture a distant star sitting behind a compact object. If that object is a normal star or a black hole, you know roughly what to expect. A brightening as the object passes in front, maybe multiple images or rings. Einstein rings, if alignment is perfect. These patterns of magnification and distortion are things we've seen many times. But a wormhole mouth could have a different gravitational fingerprint. Depending on its mass distribution and how its geometry connects to the other side, it might lens light in unusual ways, producing patterns that don't match any normal star, black hole, or dark matter clump. Perhaps you'd see a central dark spot surrounded by a ring of light that's slightly off in brightness, or pairs of images that don't behave as they should when the object moves. In some theoretical models, a wormhole might mimic a black hole in some respects, but produce distinct lensing signatures that careful analysis could tease out. You imagine one of the screens in front of you flickering with a light curve, a plot of brightness versus time as some compact object passes in front of a background star. The line rises, dips, then rises again in a way that makes the observers lean closer. They start comparing the data to models: black hole lenses, neutron stars, free-floating planets. Each known category has a repertoire of shapes, like musical phrases. If the observed pattern refused to fit any of them, a tiny whisper of possibility might slip into the conversation. Could this be something stranger? But lensing alone is tricky. So many things can imitate so many other things in the sky. Multiple lenses along the line of sight, complex motions, messy backgrounds. Astronomers are cautious by nature. They prefer several lines of evidence converging. So you move to another room in your imagined observatory, this one filled with the delicate hum of instruments, listening not to light, but to ripples in space-time, gravitational waves. You picture two very compact objects in orbit, maybe a black hole, maybe a wormhole mouth. As they dance closer, their motion shakes the space-time around them, sending out waves that detectors like LIGO and Virgo can pick up as tiny, rhythmic stretches and squeezes of distance on Earth. For a conventional black hole merger, the waveform, this rising chirp in frequency and amplitude, is distinctive. But if one of the objects were a wormhole, subtle differences might creep in. Some theoretical studies suggest that mergers involving wormhole-like objects could produce echoes in the gravitational wave signal, faint, delayed repetitions after the main event, caused by waves bouncing around inside exotic geometries before escaping. You imagine the main chirp sounding if you could hear it as a rising whoop. Then, a moment later, a softer, ghostly whoop echo, and another, fading out like ripples on a pond after a stone has sunk. In the control room, analysts would stare at their data, running matched filters and statistical tests, asking whether those tiny bumps in the noise are just random static or something more. It wouldn't be easy. Real data are messy, detectors are imperfect, and the universe is generous with sources of confusion. But in principle, certain departures from the expected black hole signature odd merger dynamics, strange post-merger behavior, could hint that one of the objects has a structure more like a wormhole than a simple horizon. Back at your imagined desk, you rest your chin on your hand, watching the streams of data flow by. The key word, over and over, is indirect. You're not going to see a wormhole glowing in neon. You're going to see its gravitational influence on light, on orbits, on waves, and then test whether those influences can be explained by more ordinary means. Only when every conventional explanation fails, and only if a wormhole model fits the data well, would the idea begin to move from wild speculation towards serious candidate. You might think of it like tracking an invisible animal in a forest. You don't see the creature itself, but you see footprints, broken branches, subtle changes in the patterns of sound. At each step, you ask, is this just wind? Just another deer? Or is there a new kind of presence here? For wormholes, the footprints are distortions of space-time itself, and the forest is the entire cosmos. Closer to home, tests of gravity within our own galaxy could also, in principle, reveal wormhole-like behavior. Precise measurements of stars orbiting unseen companions, like the stars near the supermassive black hole at the center of the Milky Way, might show anomalies that don't match any known mass distribution. A wormhole mouth masquerading as a massive object might induce orbits with subtle quirks, precessions, timing irregularities that stubbornly resist explanation. But again, the universe is adept at imitating itself. Disks of gas, clumps of dark matter, magnetic fields, all of these can complicate the dynamics. That's why, as you lie there with your eyes perhaps closing and opening in slow blinks, you can feel both the excitement and the humility of the search. Detecting a wormhole would be like solving a cosmic detective story, where almost every clue has multiple plausible interpretations. So far, every suspicious signal we've found, odd lensing events, strange transients, unusual gravitational wave candidates, has ultimately fit within the framework of black holes, neutron stars, and conventional astrophysics. That doesn't mean wormholes aren't there. It just means that if they are, they're either very rare, very well hidden, or indistinguishable from other things with our current tools. You might actually find that reassuring. The sky you sleep under is not a chaotic tangle of uncontrolled gateways. It's a place where most things behave in ways we can model and predict, where your GPS works because gravity follows rules, where the orbits of planets can be forecast centuries ahead. Wormholes, if they exist, are subtle guests in this orderly cosmos. Still, there's a quiet beauty in the fact that our detectors are now sensitive enough to even pose the question. A century ago, wormholes were just mathematical curiosities buried in equations. Today, we have instruments that can feel the passing heartbeat of colliding black holes a billion light-years away, and telescopes that can trace the bending of light around massive objects with exquisite precision. We haven't found a wormhole, but we've built the beginnings of a toolkit that could, someday, reveal one. As you sink a little deeper into your pillow, you can imagine a future night in some observatory control room when, after years of false alarms and careful skepticism, a pattern appears that refuses to fit, a lensing event with no ordinary model, a gravitational wave chirp with unmistakable echoes, a set of orbital motions that line up, cleanly and relentlessly, with what a wormhole would produce. The scientists go through their checklist, ruling out bugs, miscalibrations, mundane explanations. Step by step, the extraordinary begins to look necessary. Whether that night ever comes or not, the search itself is a kind of lullaby, humans pointing delicate instruments at the sky, asking patient questions, letting data answer slowly. Maybe the universe will one day show us a true gateway. Maybe it will simply keep teaching us about black holes, dark matter, and the ordinary, astonishing power of gravity. Either way, The act of listening, of trying to see the invisible, reminds you that the quiet darkness outside your window is full of structure, pattern, and possibility. That even as you fall asleep, telescopes and detectors are awake, watching the same universe you're dreaming about. Maybe the universe just loves to hide its strangest features a few layers deep, rewarding not only imagination, but also careful attention, the kind that turns faint ripples and tiny flickers into stories about tunnels, bridges, and the shape of reality itself. By now you've wandered through equations and tunnels, time loops and quantum threads, and yet, if you're honest, the first time you ever heard the word wormhole probably wasn't in a physics paper. It was on a screen, or in a paperback with a glossy cover, or in a cartoon where spaceships swirl into glowing funnels. Tonight, you drift gently into that borderland where science meets story, where wormholes are less a technical term and more a shimmering doorway in the dark. You imagine yourself on a couch, younger, eyes wide, room dim except for the flicker of a film. On the screen, a ship hangs over a spinning disk of light, or a ring of polished metal floating in space. Music swells, colors deepen, and someone announces, with a mix of dread and excitement, "We're going through the wormhole." The effect is all swirling clouds and stretched stars, like diving into a luminous whirlpool. You can almost feel it now, a phantom sense of acceleration in your chest as you remember. In these stories, wormholes are usually obedient servants of the plot. Need to get from one galaxy to another before the second act, step through a portal, need to meet your older self, or visit a lost civilization billions of years in the past. Just dial the coordinates. The tunnel opens on command, stable and generous, with just enough turbulence to look impressive. Exotic matter never gets a line of dialogue. Energy conditions are distant, forgotten relatives. You let those images play softly in your mind. The stargates, the swirling tunnels in animated shows, the spinning black discs from serious-minded films. They often look like whirlpools in water or storms in clouds, because that's what our intuition reaches for when we try to visualize whole in space-time. It's a comforting kind of wrongness, familiar shapes applied to unfamiliar physics. Then you gently overlay a quieter, more accurate image. The Morris Thorne wormhole you walked through earlier, with its smooth, quietly curving throat, no lightning, no roaring vortex, just geometry. In that scientific thought experiment, the attention is on tidal forces, proper time, and energy densities, things that never get mentioned in movie trailers. You notice the contrast, like comparing a roaring campfire on screen to the gentle warmth of a candle by your bedside. Every so often, though, fiction gets invited a little closer to the equations. You picture a different scene now, one from a movie like Interstellar, a spherical wormhole hanging near Saturn, the stars behind it distorted into a strange, mirrored bubble. That looked less like a tube, more like a glass marble warping the sky, is much closer to what general relativity suggests. For that film, physicist Kip Thorne actually worked with visual effects artists, giving them real equations to render how light would bend around such a structure. You imagine standing on the ring-shaped station in that story, gazing at the wormhole. The stars inside its circular outline look wrong, stretched, doubled, magnified in odd ways. It's beautiful, but in a different register than the chaotic swirls of older depictions. It hints that the universe's strangeness might be subtler and more symmetrical than storm clouds and funnel plots. Fiction also plays freely with the time travel implications you explored a moment ago. Characters leap into the past, meet their ancestors, or send messages to their younger selves by whispering through wormholes. The paradoxes are often embraced rather than feared. They become the emotional heart of the story, where regret and longing and second chances take physical form as loops in time. In reality, as you felt, the possibility of paradox triggers caution and complex conjectures about chronology, protection, and consistency. But in stories, those rules bend more easily. Scenes of someone racing to stop their own message from being sent, or struggling with the knowledge of a future they can't escape, are vivid ways to explore human emotions. Guilt, hope, the desire to fix what's broken. The wormhole becomes a mirror, reflecting not just space-time, but the way we wish time itself would sometimes show mercy. Lying there, you can feel how these fictional wormholes have shaped your intuitive expectations. When you first learned that real physics demands exotic matter and stability conditions, it might have felt like someone turning on the lights in a theatre. You see the cables, the set walls, the painted backdrops, part of the magic evaporates. But another kind of magic appears, the realization that scientists, too, are storytellers of a sort, using math instead of CGI to explore what if. You might think of a science fiction writer sitting at a desk, late at night, a mug of something warm nearby, sketching out a universe where wormholes are as common as highways. On another desk, in another city or another century, a physicist leans over a notebook, sketching the metric of a traversable wormhole, worrying about energy conditions and tidal stresses. Both are playing in the same sandbox, with different rules. The writer is free to prioritize emotion and imagination. The physicist is bound to consistency and evidence, yet they often inspire each other. In fact, sometimes story feeds directly into science. A child watches a show about warp drives and wormholes, grows up, studies physics, and ends up publishing a paper on exotic spacetimes. A scientist writes a popular book explaining wormholes, and a filmmaker reads it, building a movie around a more grounded depiction. The line between sci-fi nonsense and serious speculation is not a brick wall. It's a gradient, with ideas moving back and forth, being sharpened or softened along the way. You might remember that many of the terms we now treat as ordinary, like black hole, once belonged more to imaginative metaphors than to everyday language. Wormholes live in a similar space, halfway between mathematics and mythology for most people. They're a place where you can project fears of isolation and hopes for connection, the wish to bypass loneliness, to leap across distance, to undo time's more painful choices. As you feel your own body sink deeper into the mattress, you may notice how, for you, wormholes are now layered. On one layer, you still carry the cinematic tunnels of your childhood, colourful, noisy, simple. On another, you now hold quieter images, the Einstein Rosen bridge that collapses too quickly, the traversable throat supported by exotic matter, the quantum threads of ER equals EPR. And on yet another layer, you hold the emotional meaning those images have picked up from countless stories. That layering is not a problem. It's part of being human. You navigate the world with both myth and math, with bedtime tales and textbooks. Wormholes happen to be a place where those two ways of knowing come very close together, both staring at the same mysterious possibility. Maybe far isn't as final as it seems. You might find it soothing to realize that you don't have to pick a side before you fall asleep. You can enjoy the impossible ease of fictional wormholes, the instant jumps, the dramatic rescues, the heart-tugging time loops, as long as you remember they're governed by narrative needs, not Einstein's equations. And you can respect the sober, constrained elegance of real wormhole physics, even if it never yields a single actual tunnel you can fly through. Maybe, in some sense, the most important wormholes we've built so far are the ones between disciplines and imaginations. Bridges from physics to storytelling, from chalkboard to cinema, from the cold clarity of equations to the warm, blurry space of feeling. They let ideas travel, evolve, and come back richer. Maybe the universe just loves that interplay that we, tiny specks on a small planet, can take its quiet, geometric whispers and turn them into glowing circles in the sky, into bedtime tales about crossing the impossible distance between one heart and another. And as your thoughts slow, you can let both kinds of wormholes coexist peacefully in your mind. The strict and the dreamy, the real and the imagined, all of them gateways of a sort, helping you drift a little further into the gentle dark. By now, the word wormhole in your mind isn't just a glowing ring in space. It's a whole landscape of ideas, collapsing bridges and carefully tuned throats, quantum threads and cautious time tricks, natural tunnels that probably don't exist and fictional ones that certainly do. As you rest there, breathing slowly, a softer question rises beneath all the technical ones. What does all of this mean for how you think about reality itself? You start where your journey began, with space-time as a fabric that can bend. Before Einstein, space and time were mostly a stage, fixed, rigid, absolute. Things happened in space and during time, but the stage itself didn't participate. Wormholes, even just as mathematical possibilities, pull that old backdrop forward, revealing it as something dynamic, alive with curvature and connection. You don't live on a flat grid with a ticking clock. You float in a medium that can fold, twist, and at least in the equations, link distant places together. You can feel a tiny echo of that when you pay attention to gravity pressing you gently into the mattress. That familiar weight is a sign that space-time isn't straight here. Earth bends it. The leap from falling apple to tunnel through reality is huge, but it's built on the same insight. Wormholes are like the extreme edge of a truth you already touch every day. Where you are and how you move depends on the geometry of the universe, and that geometry is not fixed in stone. Then there's the role of limits. Wormholes seem, at first, like loopholes in the cosmic rules, cheat codes for distance, time, and causality. But the more you've drifted through their theory, the more you've met constraints, energy conditions, quantum inequalities, chronology protection, instabilities that snap shut any careless attempt at a shortcut. Instead of dismantling the rules, wormholes have forced physicists to understand them more deeply just to ask whether a tunnel can exist. You have to know exactly how matter, energy, and quantum fields are allowed to behave. You might think of it like pressing on the boundaries of a bubble to see if it pops. The act of pushing doesn't always break the bubble. Sometimes it reveals how strong the surface really is. Wormholes play that role in physics. They're extreme thought experiments that test whether our theories are self-consistent. In trying to design these tunnels, scientists discovered where classical energy conditions fail, how quantum fields enforce new kinds of averaged limits, and where relativity alone isn't enough without quantum input. That tells you something quietly profound. Reality isn't just a list of separate laws. It's a network of constraints that support each other. Gravity, quantum theory, thermodynamics, causality. They're all tied together, so that when you tug on one, the others respond. Wormholes show you those ties in a dramatic way, like plucking one string of a harp and hearing the whole instrument resonate. You also learned, in that detour through ER equals EPR, that the line between space and information might not be as clear as it seems. The idea that entanglement, a purely quantum notion about correlations in measurement outcomes, could be related to wormholes. A geometric structure in spacetime suggests that reality might be built from relationships more than from isolated pieces. Distance, in that picture, isn't just how far apart things sit on a ruler. It's a measure of how strongly they're connected in the underlying quantum web. As you lie there, maybe with your phone, a short reach away and distant friends just a message apart, you can feel a human-scale analogy. Physical distance matters, but so do connections. Someone on another continent can feel close. Someone in the same room can feel emotionally far. In a very different, non-sentimental way, wormholes and entanglement hint that the universe itself might prioritize connection patterns over simple coordinates. There's another lesson tucked inside the time machine worries. When you imagined sending messages into your own past, the universe seemed to flinch. Paradoxes appeared. Quantum fields threatened to blow up. Chronology protection whispered against closed time-like curves. Wormholes taught you that causality, the simple rule that causes come before effects, isn't just a philosophical comfort. It's woven into the structure of physical law. Time can bend, clocks can disagree, but the story still has to make sense. That gives a new weight to your everyday experience. You move through life with a quiet trust that what has happened can't unhappen, that you can learn from the past but not rewrite it. Wormhole physics doesn't overthrow that. If anything, it reinforces it. It says that even in the wildest permissible geometries, reality seems to fight against contradictions. The universe behaves less like a chaotic collage of timelines and more like a carefully edited story, where loops are allowed only if they don't break the plot. Perhaps the most gentle insight, though, is about scale and humility. On human scales, the universe feels huge, unyielding. The nearest star beyond the Sun is over 4 light-years away. Our fastest probes would take tens of thousands of years to get there. Wormholes tempt you with the thought that this vastness might be negotiable. But the more you understand about what they require, exotic matter, extreme precision, cosmic energy budgets, the more you see that shortcuts, if they exist at all, are not cheap. It's as if the universe is saying, yes, there may be extraordinary paths, but you must earn them through extraordinary understanding. That can be oddly comforting. It suggests that you live in a cosmos where progress is real but not trivial, where deeper capabilities come only after deeper insight. It hints that the gap between where you are and where you dream of going isn't meant to be bridged overnight, by anyone. You might also notice how wormholes blur the boundary between real and useful fiction. No one has ever seen one. They may never exist in our universe in a form you can travel through. And yet, by taking them seriously in equations and thought experiments, physicists have learned more about gravity, quantum theory, and the limits of technology than they would have otherwise. Wormholes show that even hypothetical structures can be tools for understanding, as long as you're honest about what's proven, what's allowed, and what's pure speculation. That honesty is a kind of quiet discipline. You can let your imagination roam ships through tunnels, civilizations tending cosmic gateways while keeping your feet firmly on the ground of what the math and experiments actually support. You've been doing that all along tonight, sliding between wonder and rigor, between visual metaphors and careful conditions. Wormholes demonstrate that those two modes are not enemies, they're partners. The awe pulls you forward. The discipline keeps you from getting lost. As your breathing slows and your thoughts begin to soften at the edges, you can gather these lessons into something simple. Reality is more flexible, more interconnected, and more deeply constrained than it first appears. Space and time are not rigid, they're responsive. Connections matter as much as positions. Shortcuts, if they exist, live at the intersection of many laws, guarded by limits that protect coherence and causality. And you small, temporary, lying in a dark room under an ordinary patch of sky are capable of thinking about all of this. Your brain, made of atoms born in stars, can imagine tunnels through space-time, test them with equations, and weigh what they imply about the world you move through every day. That might be the most quietly astonishing wormhole of all, the bridge between the universe out there and the understanding inside your mind. Maybe the universe just loves that bridge that a being made from its own particles can fold vast ideas into a single moment before sleep, feel them as both science and story, and then let them drift away into dreams. You find yourself once more at the edge of a wormhole, an imaginary one, drawn now not on a chalkboard or a movie screen, but in the soft, private darkness behind your eyes. The tunnel is no longer surrounded by control panels or crowded with equations. It hangs alone in a quiet patch of space, a dark, round mouth encircled by starlight, the way a pool of still water is framed by moss and stone. You hover there, not as an engineer or a time traveller, but simply as someone who has walked through a long story. Behind you lie Einstein's curved fabric, collapsing bridges, exotic matter, quantum threads, time tricks, paradox protections, and the long, careful searches of astronomers. Each of those ideas has left a faint glow in your mind, like distant towns seen from an airplane at night. But here, at the mouth of the tunnel, the details begin to soften. You can still recall the most important pieces. You remember that gravity is the curvature of space-time, that the weight you feel on your bed is a small expression of the same geometry that might, in extreme configurations, form a wormhole throat. You remember that, to keep such a throat open, the equations seem to demand exotic matter, with negative energy densities that only appear in subtle quantum effects, never in the solid, familiar objects around you. You remember, too, that if one mouth could be accelerated and time-shifted relative to the other, the wormhole might become a kind of time machine, and that this possibility dragged causality into the conversation. The universe, through quantum field theory and conjectures like chronology protection, seemed to whisper, "Be careful. Loops in time are not to be taken lightly." You saw how time could stretch and skew, but still resist contradictions. And then there were the quantum threads, entanglement, and the ER equals EPR idea that suggested spacetime itself might be woven from invisible relationships. You imagined tiny wormholes linking entangled particles, not as practical tunnels, but as a dual language for the same deep connection. In that picture, distance becomes less about meters and more about patterns of correlation. The universe starts to look less like a cold emptiness and more like a web. Now, standing at this imagined wormhole's edge, you hold all of that at once, but lightly. The tunnel in front of you is a symbol as much as a speculative object. It stands for the possibility that space and time are not as rigid as they seem, that what feels impossibly far might, under the right conditions, be folded closer. It also stands for the discipline of physics, which says, yes, you may dream this, but you must test it against the rules. The mouth of the wormhole is dark, but not threatening. No swirling clouds, no screaming winds, just a subtle distortion, like heat shimmer over a road at noon. The stars behind it are bent into arcs and rings, hinting that this tunnel is really just geometry. A particular arrangement of the same space-time, that carries your heartbeat from one second to the next. You feel no need to step through. It's enough to stand here in your mind and let the presence of the possibility calm you. Around you, the larger universe stretches away. Galaxies, like faint smears of light, clusters bound by gravity, cosmic filaments threading the darkness. Somewhere in that immensity, black holes merge and send out gravitational waves. Stars swell and flare and fade. Planets orbit in slow, patient ellipses. All of it follows the same set of laws, the same invisible grammar that allowed you to even ask whether wormholes could exist. You might notice a quiet kinship between yourself and this vastness. The atoms in your body were forged in stars. The thoughts you're having are arranged by electrical signals and chemistry, but guided by those same physical principles. When you think about wormholes, the universe is, in a sense, thinking about its own structure through you. That realization doesn't need any mysticism. It's simply what happens when matter becomes complex enough to wonder. Here, at the edge of the tunnel, you let one more reflection drift through. Maybe wormholes will never be built or found in our universe. Maybe exotic matter is too constrained, instability is too fierce, and cosmological evolution too conservative. Or maybe, far in the future, some civilization will manage to coax space-time into such a shape, building a single fragile bridge between distant stars. Either way, the value of the idea is not only in its realization, but in what it teaches us along the way. Wormholes have forced us to clarify what we mean by energy, causality, stability, and even space itself. They've given us a language to talk about the extreme edges of possibility. They've inspired stories that comfort and challenge us, and they've pushed our theories to reveal more of their inner structure. Like a mountain that few will ever climb, they matter because trying to reach them changes the climbers. You stand there a little longer, feeling the tunnel's presence in front of you, the stars behind, and the weight of your own body in a very ordinary room on a very ordinary planet. Then, you let the image blur, as if the camera is starting to pull back and the focus is shifting from the wormhole to the whole calm sweep of the cosmos. And now, gently, you begin to drift into the wind down. The scene slows. The tunnel in front of you becomes less a sharp circle and more a soft, darker patch in a sky filled with quiet stars. The details of exotic matter, energy conditions, and quantum threads slip to the edges of your awareness, like distant conversations fading as a door closes. What remains is a simple feeling that the universe is vast, coherent, and quietly busy, whether you're awake to think about it or not. You picture Earth as a small, glowing marble hanging in that dark. Clouds swirl, continents sleep. On one side, night. On the other, day. People breathe, dream, and turn over in their beds. Satellites trace pale arcs around the planet, their clocks ticking a little differently because space-time is slightly curved. None of them need your attention to keep going. Far beyond, galaxies rotate with unhurried grace. Their spiral arms sweep through space over millions of years. Closer in, a star flickers, adjusting to changes in its core. A planet cools. A comet arcs along a path it has followed for eons. The laws you've been exploring, the ones that allow, forbid, or complicate wormholes, are also guiding all of that. Silently, you feel your own breathing as part of this larger rhythm. In, out, like the rise and fall of tides under the moon's pull. Like the slow contraction and expansion of a star's outer layers. Your heartbeat is a local echo of the universe's patience. You do not have to hold anything together. You do not have to solve any equation or resolve any paradox tonight. The cosmos has been running smoothly for billions of years without your supervision. The universe is still here, quietly working while you sleep. Somewhere, particles continue their quantum dances. Entanglements weave and unweave, and space-time itself curves gently around every bit of mass and energy. Whether or not there are wormholes, the fabric holds. It doesn't need you to watch it for it to stay stitched, so you let your thoughts soften even further. The wormhole mouth becomes just a dark circle, then a dot, then nothing at all. The stars blur into a single, velvety glow. Even the idea of space and time can dissolve into a simple sense of floating, held up by something steady and kind. If a stray thought about tunnels or paradoxes wanders back in, you can acknowledge it like a firefly at the edge of a field, pretty, brief, and free to go. You have followed the idea as far as you need to tonight. Now it can rest, and so can you. You are lying in a small place in a very large universe, and that universe is, at this moment, perfectly content to keep turning without your help. Gravity will keep you gently pressed to your bed. The planet will keep moving along its orbit. Light from distant stars will keep traveling, crossing incomprehensible distances, whether or not you think about it. All you have to do is breathe. Let your muscles unclench, and allow your mind to drift away from tunnels and equations into whatever dreams come next. Perhaps carrying a faint echo of curved spacetime and hidden bridges, perhaps just settling into warm, familiar scenes. Either way, the cosmos will be there when you wake. The questions will still be waiting. The laws will still be holding. For now, you can let go and fall asleep at the gentle edge of the unknown.